going to see it later. So this is basic cryptography, but it gets up to some relatively advanced stuff. And let me first see if anybody needs, does everybody have Windows? Does anybody not have Windows? Okay, you don't have Windows, right? But I think you're relatively advanced. You probably aren't going to need it. Yeah. But anyway, right, so let me, the reason I decided to teach this class is I became aware of how ignorant many people are of cryptography, because I did Android development. Well, I did Android security audits, and Android apps are just appalling. Developers just throw crypto around like a child playing with a hammer. One of the things I found is that more than half of the Android apps encrypt your password and make a local copy of it, and they store it with private key cryptography, and then they try to hide the key somewhere on the phone. Apparently unaware of the fact that Android apps are distributed with their source code, and you can just read the source code and find where they hid the key and find the key. So what was the point of that? And they provide a safe place to store secrets in the key store, but they just don't use it. And there's public key cryptography that could hide the key in a way, the password in a way nobody can find it, but they just don't use it. Anyway, so I became aware of how many people do not know the very basics of cryptography. So anyway, this is structured like a CTF, and if you don't know binary or XOR, there's some simple games here where you can play with that. I imagine most people that come here are probably beyond this stage, but anyway, these are little games you can play if you need to know these things. Where this is nibbles, 4 bits at a time, so this is 8 and 2 and 1, that's 11, and so on. And there's you can also go on to a little bit more mathematical stuff like modular arithmetic. If you aren't familiar with modular arithmetic, it's at the heart of all cryptography used for computers. So if you have 9, you have like a clock face with only 9 entries. So 8 mod 9 is 8, but minus 8 mod 9 is 1, because you can add any multiple of 9s to it, and you take it by convention to the number between 0 and 8. So that's 1, and 13 mod 16 is 13, but 68 mod 9 is 63 is 0, and you have 5 more, so it's 5. It's just what it would be if you wrap around that many times. So modular arithmetic is essential, and XOR is also important. You should get used to these things. I talked about this yesterday, but it's a fundamental issue. So the way you do XOR is if you have to put your stuff in binary. So if you have 7, you got 1 and 2 is here. And so if you XOR it, the rule is if the bits are different, you have a 1, and if they're the same, you have 0. So the XOR is 0, 1, 0, 1, and that's 5. So 7 XOR 2 is 5. And on you go. Whoa, I'm wrong? No, 8 XOR 0. Anyway, maybe there's a problem with my, so I thought I saw 4 XOR 9. Let's try that one. So 4 is here, and 9 is here. And so that's going to be 1, 1, 0, 1, which is 13. All right, now I feel better. Anyway, so if you aren't familiar with those, you can practice them here. And the last one, which may have something a little bit new, is inverses. And this will come important when we get to RSA. So 8 times 2 mod 4, you could multiply it, take 16, and then divide by 4 and get 0. Or you could take each individual argument and mod 4 it. So 8 mod 4 is 0, and 0 times 2 is 0. Now, if you want the multiplicative inverse of 1 mod 9, this is important for RSA. We're going to get there. But if the question is there is no division in modular arithmetic, and this is going to be very annoying. We're going to be taking things to power and multiplying them in modular arithmetic, but you can't reverse that, and that's why we use it for cryptography. So 1 times 1 is 1 mod 9. So 1 is its own inverse in every base. But 8 times 3 mod 9, the 8 stays 8 if you take it mod 9, and the 3 stays 3, so you get 24. That's 18 plus 6, because you divide by 9 and keep the remainder. So it wraps around twice, and you have 6 more. But the multiplicative inverse of 9 mod 10. The question is, what do you multiply 9 by to get 1? So 9 times 9 is 81, and that'll do it. That's 8 tens plus 1. So there's no easy way to find those, although there's a Cauchy theorem that makes it somewhat easier. Anyway, the multiplicative inverse of 7 mod 10, if you take 7 times 8 is 56, 7 times 3 is 21, so that's it. That's 2 tens plus 1. All right, anyway, that's basic arithmetic. I'm not going to stress it, but that's a start. And the next level is to look at basic cryptography like Caesar cipher, alphabetic substitution, and AES. And one easy way to do this is to use cryptool. So if you click on this, you'll see instructions, and you can get cryptool. And cryptool is used to teach German bankers cryptography, I think, is where this came from. And it's really very nice. It makes it easy to use a Windows graphical interface to perform basic cryptography operations. So you can choose any type you want. And if you want to do classic cryptography like the Caesar cipher, you can run it here. So let me bring this up. I've got my Windows machine here. Oh, that's right, I'm zipping it. So I don't think I'm going to go through this one live. I'm just going to mention it because I want to move on to the more advanced topics. But you get a example ciphertext, and it deciphers to this. It's a quote from Caesar. And the point is, the Caesar cipher just shifts everything forward a certain number of letters in the alphabet. And it's generally only used for letters, not numbers and other bytes, although you can extend it for that. And this cryptool can do it by frequency counting, which is very nice. Because the letters are not all equally likely. In English, E is much more likely than T, A, O. So you can very quickly solve all substitution ciphers like this one by counting the letters, even in a relatively short sample. All you need is a paragraph or two to have enough letters for this frequency analysis to begin working pretty well. So you can use that, and I have a couple challenges here. You can decrypt this, and if you do, you get on the winner's board by decrypting these. You can also just do these with online tools, or you can write your own Python script. There's many ways. These are very common. So I just want them to be here, and there is no certification and no particular goals here. I'm here to meet your needs, especially in such a small class. So I want each of you to find a level where you're doing something interesting. And if it's too easy, just skip ahead. If you want to spend all the time in the beginning stuff because it's new to you, that's fine too. I just want everybody to walk away knowing a little more than they came in, is all I want. Now, you can also crack AES to some extent. Now, AES is modern strong encryption, and there is no way to crack AES if you don't know the key. That's the whole point of it. However, if you know part of the key, you can do brute force attack through the rest, and that's what cryptool will do. So here's AES. You've got some kind of ciphertext to analyze, then you've got a key pattern, and you can fill in a key where you know some of the bits and put stars where you don't know the bits. So in the artificial unlikely case that you know part of the key, then you can do a brute force attack through what's left. And it will do that and find your decrypt things. So there are some examples here. And the only other interesting thing there is the mode, which we're going to get to a little later. But I want to get down to here, and then I'm going to stop and make sure everybody's on the board. This is the one that a couple people worked on yesterday, but this I think is important enough to get started. Python runs in every operating system. So let me demonstrate this one in Python. Let's just make this big. All right, downloads, and then, all right, let's go in there. Okay, so get down to a few crypto tricks here. The first one is doing XOR online. But first we're going to do password hashes. So the whole reason why Python is so easy is because there are libraries that do all the work for you. So if I nano hash1.py and put it here, this is something, all this does now is import a hash library and then calculate an MD4 hash. Unfortunately, Microsoft Windows password hashes use one round of MD4, which is outrageous. It is more than 1 million times weaker than what Apple and Linux use. But the reason it does that is because Microsoft developed it in 1993 before MD5 was invented. So at the time, it wasn't that bad. But what's outrageous is they never updated it. So This will read a password from the user, and when you hash it, it will print the answer. But the answer, since Python is an object-oriented language, the answer is actually an object that contains various data structures. It's a data structure containing various elements, and that's not what I want. What I want is just the hex digest. So I have to add two things to my script here. I have to put in hex digest to get the raw hexadecimal value. And now if I run this one, it now gives me a proper hexadecimal looking hash. But if you compare that to the real hash from Windows machine with the password, it's wrong. And the reason it's wrong is because Microsoft is an international language, an international operating system, and they support other languages than English. So you have to use Unicode, 16 bits per character, not 8 bits per character. And so you do that with encode here. And the description of the thing you're using is UTF-16LE. So once you've done that, you should get accurate Microsoft Windows password hashes. And if you put in password, you get 886, and that's the right answer. All right, 8846. That's the actual Windows hash. Now, if you have Windows hashes and you steal them, which is how I got the ones you'll do in the challenges, you can crack them by just Googling, because Microsoft never updated their system, and there is no salt. So if two people use the same password, they have the same hash. So for the last 25 years, everybody has published dictionaries of password hashes, and they're all searchable online. So you don't even really have to use any advanced tool most of the time to crack Windows password hashes. They might as well be stored in plain text. It is very strange that they never updated it, but Microsoft is a very strange place. So if you haven't done any password hashing, this is a good thing to start. And I have challenges here where you crack some Windows hashes and log in and get points for getting in these accounts. This is the way Microsoft Windows password hashes look. You have the username, then you have this first hash that is always AAD, because that is an older system called LM hashes that is so terrible even Microsoft won't use it anymore. And there's just an empty placeholder now. And the last part here, starting out after the colon, that's the actual NTLM hash, which is one round of MD4. So anyway, there's some challenges here where you can crack some of these and you get on winners boards and you get points. And as I said, that's something some people did yesterday. Now I'll briefly go through this one, and then I want to talk about that one. Then I'm going to go around, because this is another one that's a couple people saw yesterday, so I don't want to slow it down too much by going over it. But remember, we talked about XOR. I already showed you this. And XOR is not by itself a very strong encryption procedure, but it is a component of strong algorithms. They almost all use XOR at one place or another. And so you need to understand it. So here's how you do an XOR in Python to read a whole file and encrypt it. And Python runs in every OS, so it's an easy way to do it. So let's see if I already have it here. I don't, so let me get XOR 1.py and put in that stuff. All right, so what this does, it has the shebang line, which tells it how to run Python, and I discovered yesterday on my Mac, it prefers to have it that way, because I might have more than one version of Python installed or something. Then you import the library sys, it gives you a help message. So this program is going to run from the command line with XOR name of the program, input file, an output file, and a key. The key is a single character. This is single character XOR, which is not very secure, but it's a way to get started. And so it's going to just XOR every byte of the file with K and write it into the output file. So it opens the files, reads the bytes one by one, uses this character to XOR it with K, and then writes it all out to the other file. That's all it does. So you have to make it executable. All right, and now if you run it, it'll tell you you have to give it an in file and an out file. And if you take plain text, I'm going to just do this one here, plain text with just an A in it. The point of that is, to make the simplest case, if I print plain one, it prints an A, and there's not even a character return after it. It's a one-character file. So now I can use my script to encrypt plain 1 and put it in cipher 1. And for a key, I'll use a lowercase s. And now if I cat cipher, it's a 2. So A, capital A XOR lowercase s is 2 in ASCII. And you can see that if you go through the ASCII. And so this is, if you make a normal file with readable text in it, let's do nano plain 2 and say hello. All right. It really does. This is why a lot of people use this, even though it's not very strong, because it certainly does scramble things pretty well. Plain 2 to cipher 2, encrypt that with something like S. And now if you cat cipher 2, it turns into complete garbage. And a lot of the characters turn into non-printable characters. So, you know, it does scramble stuff. The problem is, the only problem with this system is with a single byte key, I have a very small key space. There's only 256 possible bytes, so you can just try them all. And that's what you'll do. So there's some challenges down here where you decrypt a text file, where the key is just from A to Z, and then you decrypt a text file with the key just from 0 to FF, all possible single byte keys, and then you decrypt an image. Now when you one issue in all cryptography cracking is if you can try all possible keys, you can crack every cipher except for the one-time pad. The problem with the one-time pad is it has a different shift for every letter, and all possible combinations can be there. So when you run a brute force attack, you will construct all possible documents with those many letters. So you can't tell which one is right. Normally what happens in cryptography is you have a low entropy system, which means you can find one that is readable or usable, and all the rest are just garbled nonsense. But in the one-time pad, you create every possible file, and you don't know which one is the right one. But anyway, that's what happens here. If you have readable text, only one of the shifts will make anything readable, so you can spot it. And in this case, you can tell when you get the right one because image headers always have certain bytes you can rely on. So ping files always start with .png, and there's another one down here where you do a JPEG file, and that always has a JFIF over here in the header. So you look for that. And this is the same way you do a lot of decryption. You have to have some way to tell when you win. Anyway. So those are ones you can try, and the one I want to work through in a little more detail is the one that is new here, which is this ECB versus CBC mode. This is a very famous issue and an important thing to know about cryptography in general. The kind of cryptography I've talked about so far is called textbook cryptography, and people sneer at it because you can't really use it safely for real-world work. Because Microsoft did, for example. They have this password hashing algorithm, just one-to-one correspondence between passwords and hashes, and that is very unwise. That means you can make a dictionary of known password hashes and crack passwords. They should have added a random bit before hashing it, and you'll see there's a similar issue here. DES was the government's first encryption routine they approved, and they defined 4 or 5 modes to operate it in, and those modes are still used by strong modern cryptography like AES. And the most important ones to consider are ECB and CBC. Electronic codebook mode does what Microsoft password hashes do. It has one block of input encrypted with a key to make a block of output. And if you have another block of identical input, you get the same answer for the output because it just applies an encryption routine and it doesn't add any varying quantity to each byte. So that is actually a pretty terrible thing to do. And you'll see why here. If you download this image, let me open my, this I can close now. Let me open my file here so we can play with that image. I go to downloads and CH, all right. So that thing is tux.bmp. There's that picture of a penguin. All right. Now, I can encrypt that thing in ECB mode. Remember that I said the reason you love to use, all hackers love Python is you don't have to do any work because someone else has already written libraries that do everything for you. All you have to do is figure out how to load and run the library, which is a pretty small task. So I'm not even going to make scripts here. I'm just going to run Python in immediate mode. This is when I first learned programming. I had a Commodore VIC-20, and I just typed BASIC in here and did everything right there, line by line, and that works fine. So you can do simple tasks that way, again, in Python. So I can import AES, which is the modern encryption system that you can trust. It needs to have a key. I'm just going to use that key because I don't really care. I just want to see how it works. And then I can create a new AES object based on that key. So now I can read a file in with just a couple of commands. This will read in that tux.bmp file. And so now I have an object called clear. If I were to try to print that, I could print like the first 10 bytes of it. And it's just sort of unreadable junk, but you may notice the file header starts with BM. Almost all image files start with a header. There's JFIF near the JPEG, and this starts with BM to tell you it's a bitmap, but the rest of it is unprintable binary, so you just get question marks and foolish characters. All right, so now I can encrypt it. This is all you have to do. I created an object named cipher that is an AES object based on the key, and by default, AES uses electronic codebook mode. And in electronic codebook mode, the only thing you need is the key. There is nothing else. It takes blocks of input, and it encrypts them one by one with the key. And if another block of input is the same, you get the same answer. So I encrypt it with this. This will just create an object called ciphertext. Now, the only problem is AES does it in blocks of 16 bytes. And if you don't have an integral multiple of 16 bytes, it gets upset because there's a couple bytes at the end and it doesn't know how to encrypt anything. So in this case, what I'm going to do is just cut out, make clear trimmed, which will trim out most of it. Because remember, if I encrypt the whole file, I'll also encrypt the header, and nothing will be visible. And that would be okay if I was going to encrypt this and store it and mail it to somebody and they would decrypt it. But in this case, I want to actually look at what the encryption does in the image viewer. So I want to preserve the header and encrypt only the data. So I don't really need to encrypt every byte. I'm content to encrypt everything after the first 64 bytes and not encrypt a couple bytes at the end, because I'm going to look at the middle of the image and see what it did. So I'm going to create an object called clear trimmed that is everything after the first 64 bytes and skipping the last 2, which is most of the data, and then encrypt that stuff. So this will make that stuff ciphertext. And now I can create the file by taking the original unencrypted 64 bytes at the start, which will include the file header, then putting in the encrypted stuff, and then putting in the last 2 bytes of the original file. This is a simple way to create an image I can view where the internal part of it is encrypted. So that creates this file called tuxecb.bmp. And if I look at that file, that is this one. Okay, and that's the point. This is what electronic codebook encryption does. Since I have blocks of solid color, like all this white, each one of them turns into this pattern of pink, and you still can see the shape of the penguin. So normal people are not content calling this encryption. The point of encryption was to hide the contents of the file, and it hasn't really hidden the contents of the file very well at all. This is the problem with electronic codebook mode. So this textbook encryption process is dangerous. This is the same problem Microsoft has. If identical input leads to identical output, then you leak data through your encryption process. So this is why people use CBC mode. Cipher block chaining is the most popular solution to this problem, although it causes other problems. But the way cipher block chaining works is you encrypt the first block, and you take the output and use that as and add that to the next block before encrypting it. Then you encrypt the next block, take the output of that, and add it to the next one. This means you can't do it on a parallel computer anymore. You have to do the blocks in order. It also means that the result of each block depends on the encryption of the previous block, which is going to lead to a disaster later in the padding oracle attack, but that's the way it's really done. It seemed to me like counter mode is the mode that should have become popular, where you just have a number 1, 2, 3, and 4, and add it to each block, or you have a pseudo-random sequence. Then you could do it in parallel, and each block would not depend on the block before it. But for some reason, cipher block chaining became the standard. Yeah.
That's a very interesting point. Why do you think you find that today, even when you look at the industry accepted ciphers, you're still with BSidesSF?
Oh, well, I have a lot of faith in mathematicians. So I would assume that cipher block chaining has some esoteric advanced mathematical advantages. but it does have weaknesses. And they'll do
like related key attacks.
like which?
The related key attack.
Related key, I don't know that. That word attacks cipher block chaining also? Yeah, I'll have to look into that one. I know the padding oracle attack, but I think the point is every crypto system has a bunch of attacks and a bunch of weaknesses. That's like one problem in cryptography is it's fragile. When you actually implement it, if you make any questionable design decisions or little mistakes, they're often enough to leak the key. Like often the power consumption of the computer leaks the key, the radio signals emitted, the time it takes to encrypt. And in the padding oracle attack, it's an error message. If the error message gives you too much information, you get in. It's just, it sounds good on paper and the math is beautiful. When you actually implement it, it is very easy to make a fatal mistake. That's why it's worth paying for real cryptographers that actually learn some of this stuff. And it's worth us all trying to learn whatever we can of it to help guide people not into making the same mistakes over and over. Because the fundamental mistake here that Microsoft made, where they didn't salt things, they didn't have something that buried added to each byte. They made that mistake over and over and over. It was also true of Microsoft Word documents encrypted before the 2008 version. And the reason they kept making that mistake over and over is because Microsoft Windows is like a Frankenstein monster. It's not written by one team. People write, companies invent stuff, and Microsoft buys the company and engulfs them and builds that product into Windows. So they get many different teams designing stuff, and there are just trends. I remember in the 90s, I worked with financial data, and we just emailed it unencrypted all the time. Word documents and Excel spreadsheets. Nobody was aware of the risk. I was the first guy at my company to say we should be encrypting that, so I made them all use Microsoft Word encryption, which was broken, but I didn't know that either. And you know, you go through generations. I mean, whatever you're doing now, in 10 years, they will say, oh, what fools they were. How could they have done that horrible thing? That's just the way it is. Yeah. Yeah.
Depend, again, I'm not very clear about it, but I was just wondering if you have any opinion. But
yeah.
So it does depend on the pseudo-random generator.
Well, it's often not pseudo-random. You can just use 1, 2, 3, 4. And I really
wouldn't that possibly be a pattern?
Well, it is a pattern, but as far as I know, having a pattern in the initialization vector is harmless, but maybe not. That's why I'm saying there probably are, you have to read the advanced mathematical theorems to understand the real risk. But yeah, that's a good, yeah. If there is a problem with the IV being predictable, then that's a problem. Anyway, so let's do this one. So this is the fix. This stuff is now encrypted. And now I want to view the file. I want to encrypt it with a better system. So let's make a new one. And here we're going to encrypt it with CBC mode. Now this is cipher block chaining mode. And in order for cipher block chaining to work, you have to feed in an initialization vector. I don't really know why, but I guess they don't even want to do the first block in ECB mode. So you feed in an IV for the first block. And all future blocks use the output of the previous block as the initialization vector, which is combined with the data before you encrypt it. So this will make a different cipher object. And now I'm going to take the clear trimmed. I don't need to retrim it because the clear text that I trimmed before is still there. I encrypt it here. And now I reconstruct the output as before with the unencrypted header and the last few bytes unencrypted and the rest encrypted. So now I have Tux CBC bitmap. And that is here. And there you are. That is what most people expect from encryption. It's just totally scrambled random junk and you can't tell what image was there at all. So that's why this is popular. It does pass the superficial test of scrambling the data. But it fails another test, and I think looking at the way things are going, I think I'll show you this one, and then I'm going to pause for a while and go around and help people do some of this. So if you got that far with CBC mode, let me go to this padding oracle attack here, which I think is fun. That's why I say CBC mode has this problem, and it's pretty easy to see what's wrong with it. So if you have, okay, here is how CBC mode actually works. A nice diagram from Wikipedia to which I added colors. So you have an initialization vector coming in. You have plain text up here in green. You have 16 byte blocks of text. You take the initialization vector, You XOR it with the plain text, then you encrypt it with the key, producing 16 bytes of AES encrypted text. Then you take the output of that and call it the initialization vector and XOR it with the next block of plain text and then encrypt it. That's how it's done. This XOR operation here is very dangerous, and it's going to give us the key to everything. So that's encryption with CBC. So suppose you have only 47 bytes of plain text. Then you can't encrypt 15 bytes, you have to pad it with a byte. Now you have to have some system of padding. And various systems have been proposed, but one system that is very common, well anyway, is put in a block of padding. Now, when you decrypt it, take a look at what happens here. In the decryption, you start with ciphertext, you put in the key and decrypt it, then you XOR it with the IV and you get the first block. Then you take the ciphertext and put it down here. So you take the next ciphertext block, decrypt it, you take the raw ciphertext, and that's the thing you XOR it with here. So this creates a connection between this block and the block before it, which we can exploit. And it turns out we can break everything with that connection. So here's the because if you have the ciphertext, that you know this, and it's just XORed here. And XOR is a very simple operation. So if all you know is the ciphertext, there's not a weakness. There's a weakness if all you know is the ciphertext and you're able to find out something about the padding. Those are the two things that have to go together. So let's go here. The problem is padding is quite simple. This is the common system used for padding. See, one issue about padding is if I put some bytes at the end, like zeros, how do I know they aren't really there? How do I know they're padding bytes and not bytes that were actually part of the original data? I'd have an ambiguity in knowing where the file ends. And that's unacceptable. So here's the padding system. If you need one byte of padding, it has to be 0, 1. If you need 2, it has to be 0, 2. And if you need no padding at all, you add a whole block of padding that's all 16s. Therefore, there is always padding, and you look at the last byte, and that tells you how many bytes to throw away. Now you know exactly how long the file is and where it ends, and the file will always be an equal multiple of 16 bytes. So that's the purpose of this padding. It makes it easy to encrypt anything and decrypt it and always get it right. The problem is, it means I know what the last byte is. There are only 16 possibilities, and once I find out, I know more. So we can play games here. If I modify the 31st block of the ciphertext, remember the normal case of the attacker, they have the ciphertext and they don't have the key and they don't have the IV, and they're trying to get in. So if I modify this byte, what happens is that scrambles this whole block of data. But it also modifies just one byte of the next block because it only affects the next block through this XOR and brings in that data. So this change only changes one byte there. So I can do, all right, so I can do that pretty easily, and you'll see it here. You can do it in Python, and you'll see. I changed this one byte, and it changes 16 bytes here and one byte at the end. So now I'm getting some control over the plain text without knowing the key. So we are going to be able to do some nasty things here. There's a vulnerable system you can import, and when you encrypt a 47-byte key, it's going to add a 0, 1 to the end here. That's the normal padding. So it puts that 0, 1 byte of padding. And now, this encryption routine, which you can just copy in Python, this contains the fatal error. If you decrypt it and the padding comes out wrong, it tells you padding error. This is something that probably most people implementing cryptography do not understand. That ruins the whole thing. You should have just said error. Because you said padding error, I now know what the problem was. And that means I can just try different bytes until I no longer get the padding error message. And now I know something that I shouldn't have known. So that's the game. So I'm not going to learn the key or the IV, and I'm not going to be able to read the message. What I'm going to be able to do is forge a message and make it say anything I want, which is often very bad too. For example, in serialized web requests, you take data, you put it in a serialized Java format or something, then you base 64 it, then you put some kind of signature on it, then you send it to the server. The server verifies the signature. If I'm able to craft a message and also craft the signature, I can fool the server, and that was what this was used for in the early versions. So suppose I want to make a message. I can't control everything about the message, but by sacrificing one block, I can control what happens, what the decrypted version of the next block is. So I can create a message that will have garbage plus part I control, and on the web, that's usually enough, because you can have parameters that aren't used, and you can have repeated parameters and so on. So here's the goal. The goal is I want to figure out this intermediate step with the block covered orange. That is the thing that I'm going to attempt to find out. Let me fit it there. Now it's fitting on my screen correctly. Okay, so I've got this 47-byte message. And I would like to learn this value, which depends on the ciphertext and on the initialization vector and all this jazz. Even though I don't know the ID and I don't know the key, I can determine that value. And once I know that value, I can put whatever I need to here to make this last block turn into anything I want. So by letting 16 bytes turn into garbage, I can create 16 bytes that say anything I want, as if I had the key, and therefore I can fool a vulnerable system into believing that I have the key when I don't. All right, and as it's a fairly simple pack, I just have to vary this byte until I no longer get the padding oracle message. Then that means I know what's here. It has to be a 0-1. So I can deduce this value. And that's what happens. So you do it in Python, it only takes a couple of lines. And if you do 5 modifications, all of them just produce padding error. So you have to try 256 modifications, and you will find that 2 of them are correct, because one of them is the actual real plain text, which probably doesn't have just 1 byte of padding, it probably has multiple bytes of padding. So there's some other byte that you can get, which is not an error, but one of these is 0-1. Where I've created a condition that puts a 0-1 at the end. And if you corrupt more bytes of the previous one, then you scramble everything over here and make sure that you're getting a 0-1. So in that case, you find out it's 147. So by just with 256 guesses, I can deduce 1 byte of that intermediate value. And I can repeat this now, knowing that, and do the bytes one by one. So by 256 times 16 guesses, which, what, 4,096 or something like that, I can find out 16 bytes, and then I can gradually have complete control of this 16 bytes. So that's what you do. You go back step by step, and you're finally able to construct anything you want. So, for example, if it's enough, just for a simple case, I wanted to make it so you put win at the end. Right now it says lose, and you can turn that into win by using these values. You can create ciphertext that decrypts like this into this garbage and then has win at the end. All right. And thought I redacted that, but anyway, I'm not going to worry about it. Shift that. All right. Anyway, there's a minor defect in my scoring system, but anyway. So I'm going to stop this lecture stuff. Let me go around and help people, make sure everybody gets on the board, do some of this stuff, and then I'll demonstrate some more stuff up here. I'm going to pause this recording. Let me jump ahead and show you one that is really very easy, but pretty exciting. You probably heard about quantum computing. The NSA had been telling us to use elliptic curve cryptography for years because it is much faster because the keys are much smaller. So it'll save a lot of power and a lot of CPU time. And about 18 months ago, they suddenly reversed course and said, forget it and go back to good old prime number RSA because quantum computers are coming and they're going to ruin everything. And it turns out quantum computers do not really do that much harm for AES. If you have AES 128, all quantum computers mean is you have to go to AES 256 and it remains unbreakable. But asymmetric cryptography is broken. Even 1 million digit RSA will not be safe. that quantum computers work. It is amazing. The whole logic of public key encryption is going to be kind of shot. And so mathematicians have been working on this, and NIST is currently having a contest to determine the new crypto system that will survive quantum computers. No one knows what it is. They have 20 submissions now, and just last week I saw a cryptographer completely destroyed one of the submissions. They figured out how to break in like 1 minute. So that's what happens every time. Every time they have a contest to bring in new crypto systems, people apply. There are about 20 submissions. About 15 of them are proven to have horrible holes. And there's about 5 finalists that are very good, and they pick one and give it the stamp of approval. And the other runners-up are also quite good. So that's happening right now for quantum encryption. But the thing that amazed me is you can do quantum computation right now. IBM has made a quantum computer available for free for everyone to use on the internet. So you can practice quantum computing. You do it here at this URL with the Q experience, and that lets you use their quantum computer. They have taken one and put it online. And all you have to do is log in with a Twitter account or something to use it. Now, you can simulate computations and you can run computations. If you run computations, they limit how much of it you use. They give you like 5 units unless you like write them a letter explaining you're really a PhD research student, you need more, and then you have to wait until you can do more. But you can simulate as much as you want. You could also download a Python library and simulate locally, but this really is the real quantum computer. So here it is, by the way. They've been carrying it around to conventions and stuff. It's a bunch of magnetic coils in a vat of liquid helium or something cooled to some very low temperature in the millikelvin range, so it's something even more extreme than normal liquid helium, and then connected with magnetism to each other. So they can be, the quantum mechanical properties of the magnetism can be connected. But here is where you get to use the editor, and you can switch to a command line mode where you program this in a language that looks like Python, or you can just program it on this music staff, which is of course even more fun. So you can take a measurement, and a measurement is this operation. So I have 5 qubits. So if I put that there, I'm measuring this qubit. Now I can simulate the effect of that. And I don't care about the experiment name. It runs the simulation, and what it does is it runs 100 times and shows you the result. And the answer is, all 100 times it gave me 5 zeros. All the bytes are 0 because I have no uncertainty here. The bits start in a certain state of 0, and if you don't do anything to them, they just stay in a certain state of 0. So I didn't do anything yet. I just measured bits that are in the state 0. If I want to do something more fun, I need to create randomness. So I'm going to move my that over, and I think it's an X that rotates things enough in the 3rd dimension to make them random. Let's see what that does. I simulate that. Nope, still, that flips it. The X flips the bit. And if you, by the way, if you want to understand this in more detail, there is a very nice tutorial about it here that shows you how to read this. I'm not sure I can find it right, but it shows you how to visualize this in the 3rd dimension. You're rotating a bit in 3 dimensions. And I think it's Z, let me get my instructions, that puts you in an uncertain state. So let me go down here, more classical measurements. There, it's all right, the X. Yeah, that's what I thought it was, the X. What did I do wrong here? All right, the X should have made it uncertain. Rude. All right. What did I do wrong? X followed by a measurement should be uncertain. All right, let's try the H. I'm going to move ahead here and not worry about it. Let's get rid. Maybe I need those other measurements. I wouldn't think I would, but just let me put them in and see if that should take me to exactly the situation I expected. All right, let's see what that one does. Oh, it's the same. That's what I thought. X is not the right one. I think maybe it's Z. Anyway, you can throw one away here, and you can play with this stuff. And there is a tutorial to explain it. Let's see what Z does. Also uncertain, no uncertainty. All right. anyway, let me make a more complicated one with the H here. And there we go. All right, let's see what that one does. All right, now I'm finally getting uncertainty in the last bit. So I have a 50% chance of 0001 and a 50% chance of 0000. So you can set up these options, and that gives me one uncertain qubit. Now you can make a circuit here, and you can entangle them. So if I put the H in the middle, I create uncertainty. Let's move it over. Get rid of this one. All right, put this in the middle and run that one. That should give me the uncertainty just on a different bit. All right, and now it's moved from 0000 to 0010. The bits are right to left, top to bottom. So the second bit from the right is now uncertain. Now, if you have multiple uncertain bits, they are uncorrelated. So you'll have many options. So let me get that one up. That is the simple case of randomness. And that is this one there. That's the one. If I just H everything, H will make them in an uncertain state halfway between 1 and 0, so that when you measure them, half the time they'll be 1 and half the time they'll be 0. And that means you have 8 possibilities, and there they are. 101, 100, 011, and so on. And those 8 possibilities are all equally likely, and this is a real random experiment, so it only did it 100 times, so there's some random variation. Approximately 1/8 of the time, each of those things happen. But now you can entangle the qubits, and this is where you get the real value of quantum computation. So move these measurements over, get them out of the way. Okay, and now we can entangle the qubits here. So if I put a plus sign on there, and I entangle this one, oh, come on, don't mess with me. I put a plus on, and I drag it down there. Now I have entangled those 2 bits, putting a connection between them. So they have to move together, both 1 or both 0. And they're both uncertain, but they're tied to each other. And I shouldn't have seen 8 options anymore. Oh, I have to get rid of the second H, pardon me. I have to not randomize one of them as well. All right. And now those 2 should be connected. There. Now I get 4 options because 2 bits are tied together. So it's it's not immediately obvious to me which 2 bits it is. But anyway, I don't want to stumble through this any further. I just wanted to show you this, and I would like to, and so you can play with this a bit and get used to it. And if you want to actually understand it in more detail, there is a very nice tutorial, which I will find and point you to if I don't have it connected on this page. Oh, here it is, IBM Beginner's Guide. Let me point to that. If you want to actually get this stuff right, this is the one that explains it in fairly clear terms. There you go. So superposition here is here. It explains you what the H gate does, and that's the diagram I wanted to point you to. You can look at this in 3 dimensions, where a pure 0 is up here, and a pure 1 is down here, and the quantum mechanic uncertain states are in the middle, which are sometimes 1 and sometimes 0. And each one of those operations, X, Y, and Z, rotated in 3 dimensions. And this is, yeah, go ahead. The 5 qubits you have here are not enough to actually do anything important. There's no quantum computer out there yet that will crack any strong encryption. The only reason everyone is panicking is because the ones that are out there now are good enough that it really looks like in a couple decades they'll work. The reason why it's not good enough now, there's 2 reasons. You need a lot more than 5 qubits. You need something like 50 or 60 qubits before you can really do something. And the second thing is, qubits are not all the same. They have to be high precision. There's a measure of noise in the qubits, and this current generation of technology is too noisy. So all you can do is like prototype demonstrations of the technology now. That's a really important question. So people are panicking, not because a quantum computer can break in now, but they're afraid pretty soon that will happen. And when the NSA warns you, my personal belief from watching them go is when the NSA gives a warning like this, What it means is they have it. They probably, because they're always 20 years ahead of the private sector. They have secret stuff. They can do stuff that we can't. And when they suddenly panic and reverse course, remember a few years ago, I think around 2007, the NSA destroyed a physical motor with a cyber attack. They called it Project Aurora. And they told all of us, you guys better watch out for attacks that will destroy physical equipment. And we all said, what are you talking about? And it turned out we were doing that to Iran secretly at the time. And there was another one like that where they warned us of something and it came out later. Oh, they warned us not malware was coming on USB sticks. They would destroy your computer, and it turned out later we were doing that to other people. That's usually what happens. So I don't know. This seems to me like it kind of violates the concept of keeping secrets. I know Europeans laugh at Americans and say you have no idea how to keep secrets. But you do things like this, which make it pretty obvious what our secret mission is this year.
Do you think that NSA is actively using quantum computing to break their person?
Yeah, I do. Really? I think they would not warn us in these strong terms unless they have one that really works. So I think we have one with 5 qubits, they got one with 100.
You think other countries do too?
No, I don't. The NSA is way ahead of it, except for Britain. GCHQ is no slouches either, but they don't have as much money, and they partner with us. No, I think the NSA is very proud of themselves, and justifiably so, that they are a couple of decades ahead on every kind of attack, especially mathematical cryptographic attacks. That is their #1 mission. I mean, have you seen the Chicago challenge? I should mention that in a crypto class. This is something you should all know. Chicago challenge. If you're willing to go down the rabbit hole and worry about crazy paranoid stuff, crypto will really justify that. I mean, when I was a kid, the hippie said there's LSD in the water and the man is listening to everything on the phone. And I said, oh, you guys are just nuts. And it turned out that was all true. And this is all true too. So if you see this symbol, that is the cicada. This is a real thing. I've played it. Every 6 months or so on the internet, this thing will appear in a random location, and you just hear about it from rumors. And when you go there, there's a web page. And when you hunt on the web page, there is a clue. And when you solve the clue, it goes to another web page. And there's a clue hidden there, and it's a game, like a CTF. And I got to maybe 4th or 5th level before it got hard and I got bored and did something else. But it turns out if you get to around level 20, they make you sign a non-disclosure agreement promising to never tell people what's beyond that, and no one ever has. And the general belief is this is recruitment for the GCHQ, the Britain version of the NSA, because there's a small number of people on Earth who are mathematicians of the type where they can solve the world's cutting-edge cryptography problems. And if you have a mind like that, you are bored by everything else. And you seek something that is not trivial and boring to you. My mother was like this, by the way. My mother was one of those people, I think her IQ was 170 or something. My mother was so smart that she couldn't even talk to people. She was pretty much isolated because we were all just totally boring to her. She was an expert in metaphysics. She was at the cutting edge of metaphysics, which was so abstract, it's hard to even understand what it is. It's the study of what is real in a philosophical sense. It's sort of hard to even grasp. But if you do that, there's nobody to talk to. You're pretty much alone. There's you and like 5 other people to talk to. And all the people who can do this stuff are there, and they're trying to find them. And this is how they find them. So the NSA and the GCHQ have assembled the 100 most brilliant mathematicians in the world, sworn them to terrifying oaths of secrecy, and given them toys to play with that are 20 years ahead of everything else. So they are doing awesome stuff. And that is their whole job. That's why, you know, when Snowden Revelations came out and they said NSA is hacking every corporation, I said, well, of course they are. That's their mission. That's what they're supposed to do. We pay them a lot of money, and we get the smartest people on earth, and we say, hack everybody and find every encrypted thing everywhere. That is their job, and they're doing it. But anyway, so this is a fun thing, and it might be out there again. It comes out frequently, and it's kind of fun to do the first few levels. No one really knows where it goes, but it pretty much has to go to NSA or GCHQ, and there's no other logical destination. So when they give us a crypto warning, I think it means they've got it working. Anyway, I wanted to point you to that quantum mechanic computation. You might want to play with that. That's a fun one. And I think I'm going to stop talking. You ought to go out and get lunch. So don't, let me freeze this thing. I'll watch, I'm going to stay here so you can leave your computers behind if you want to. Do that. All right. So I put it at the bottom of this Crypto Hero page. Here's the other similar games like this, and here's the whole courses that go with them. So the one for this class is Cryptography here. And use these two textbooks, this for the cryptocurrency, which I'm not covering today because I'm sort of less interested in it these days. And here's the Cryptography book, one of the standards. And here I've got a bunch of lectures in video and PowerPoint slides and all that jazz, and then a bunch of homework, which is turned into what you're doing. All this is a thin veneer of game on top of homework. But CTFs are awesome. They're very effective at tricking students into doing homework. I'm all for it. Anyway, so anyway, if you want the whole courses, there they are, linked at the bottom. And they've got a lot of more information in them, of course. What I did here was pick out the fun projects and gamify them. Anyway, I wanted to move on to another topic. You haven't got your money's worth if you didn't do RSA. Because RSA is fantastic. And I should actually bring up a graphical description. We go to images and get mailbox. And that's what I want. Okay. This thing right here is the best way to understand RSA and the strength and weakness of it. Public key encryption is a miracle. It solves the problem of how do you send a secret over an untrusted medium when you never have a chance to ever exchange a trusted secret. The old system, private key encryption, for example, British naval vessels had this system of flags that indicated their maneuvers in combat, and they had a secret code book. And the code book had a lead bar in the binding, and the captain of the naval ship was told, if the French catch you and they are taking over your ship, that code book has to go over the side. And if somehow you are captured and that code book did not go over the side, we will pay the ransom to bring you back to Britain so we can hang you. Because that book is worth more than you, worth more than your crew, worth more than your whole ship. Because if the French get our codes, we're screwed. And that's the problem with private key encryption. You have this secret, and yet you have to share the secret with someone, and that is intrinsically stupid. You never really know who else has been making another copy of that secret, and you don't have any good way to get the secret there. So public key encryption solves this, but it solves it in a way that is very inconvenient. You can only receive secrets. You cannot send them. So that's what the post office has. They have a box here where anybody can put in mail, but only the holder of the key can pull out the mail. That's what public key encryption is. You can make a mailbox and receive secrets. And anybody can give them to you, and you're the only one that can receive them, but you can't send anything to anybody. They have to prepare themselves by making their own secret box. And that turns out to be enormously painful. And even the people that invented PGP have quit using it because key handling is such a drag. The same thing happened to me when I used it. Everybody, you always don't have your private key. It's on my other machine, on my other USB stick. Unless you spray it all over the place so it gets stolen, you don't have it when you need it. So I have like 5 public keys out there, and people can send me mail. Good luck. I've lost all those private keys. I also lost the passphrase to cancel them. So they're just corrupting the chain, and the same thing happened to everybody else. So if you actually try to send anything to anybody using those published public keys, you're pretty much hosed. But the mathematics works very well if you have a system that does it automatically for you. Email is a terrible case and doesn't work. But HTTPS is where it works because you make the connection live, you make a temporary pair you use right now, and the only person that actually has to handle key management is the server. And they have experts doing it. I don't have to manage a key myself. I just generate a temporary key for the duration of one session. So here's how RSA works. One of the things great about RSA is the mathematics is very simple. There are only 2 hard parts, and you've already practiced with them. Really, the only hard part is modular arithmetic and modular inverses. That's why it's important to get some understanding of that. So here's how you generate the key. By the way, cryptography is always like this. It sounds good until you actually pay attention to the details, and then you realize they're pulling the wool over your eyes. So here's how it works. Choose a large random number, prime, and make it prime. Now choose another large random number, multiply them together. Okay, you've already gotten completely screwed. What is a random number? How can you actually make anything random? There's nothing random in your computer. This is an enormous problem, and there is no good solution. You can actually pay for a special hardware random number generator and attach it to your machine, And the latest version of Intel, I think the i7 has a hardware random number generator built in, but the BSD people refuse to use it because they're afraid the NSA backdoored it. And like the other things I was saying, like the paranoid conspiracy theories, that has happened 3 times that we know of. Microsoft even found one of them. They do totally lie to us. The NSA totally lies, and they pressure the National Institute of Standards into totally lying, and they pressure RSA into totally lying and building a known broken standard into their product for $1 million bribe. You can't trust anybody, and yet you can't do anything without trusting somebody. So you have to trust someone and be aware that you can only trust them so far. That's why you need threat modeling. That's why after the Snowden revelations came out, everybody said, buy our product and it'll stop the NSA, and I sure hope nobody bought that. You can't stop the NSA. This is like, hire my security company and the US military won't kill you. I said, good luck. They can't protect the president. Bin Laden can't hide from him. There's nothing that will stop the NSA. I hope to God that's not your threat model. If you're doing something that has the NSA after you, you're in trouble. I just accept the NSA being able to see my stuff and have smaller threats that I might be able to stop. So anyway, as best you can, you get 2 large prime numbers. By the way, if you do get a large random number, how do you know it's prime? It turns out to be a very interesting puzzle. And the easiest solution is there is a primality test that has a 50% chance of detecting whether a number is prime. And you run that about 100 times, and then you have a pretty good chance that it's prime, but you still don't know for sure. So what you do is you encrypt a message and decrypt it and see if it works. And at the end of all that, you say, well, it seems to be good enough. And you go ahead. All the beautiful math in practice has approximation and guesses. Anyway, so after you get these prime numbers, you then calculate n is p times q. This is your public key is n. The prime numbers are your private key, and that is what the secrecy relies on. You cannot factor a large number into its component primes without guessing every number up to the square root of the number. So for large numbers, it takes an incredible amount of time, and no one has yet ever found any way to do it fast. Although, in theory, quantum computers will be able to do it very fast. But they don't exist yet, as far as we can tell, not out in the public, unclassified world. Then you have 2 things, you choose an n and you choose e. And the e just has to be a large, odd number, and typically people just use 3 or 65,537. Those are just common values. Turns out that everybody just using the same number and using the same small number is perfectly fine, and that's what everybody does. Then you calculate this phi number, which is p minus 1 times q minus 1, and the private key is a multiplicative inverse. So all cryptography uses modular arithmetic. You have this circle, which is phi around, and everything wraps around. So your input comes in the form of bits. You take a block size. It's only got so many bits, so many possible values. And after you do encryption, it's still trapped on the ring to only have so many possible values. So everything works in rings. So here's the game. You can do this all very easily with Python. So if I do this, let me just do it all here. To see how it works, you can do it with small numbers. Of course, these are not secure, but we don't worry about that just for testing it. So now I've chosen P and Q. I chose 2 prime numbers, and now I get N, which is 161. Okay, so now I have to calculate phi, which is just P minus 1 times Q minus 1. So that's 132. Now, I choose a public exponent of E. I'll just use 5. And now we begin to have a dirty problem. Let me just make it so both of these will fit on the screen at once. All right. So I want to find something. I want to find the multiplicative inverse of E mod phi. And that is not so easy as it could be. If I take this, and I take 20 times E, that's 100, of course. Now I want to do modular arithmetic, and we talked about this. So in this case, my modulus is 132. So that means I have numbers from 0 to 131 around my clock, and then I just go around and around and around. That's my modular ring. So every possible answer is between 0 and 131, and everything wraps around. So to do that, you do a %fin. So we can just calculate some values just to see it go here. Here's a few. All right, so here 100% phi is 100, 130 is here, 131 is here, and 132 is 0, because I'm modulus 132, which means 132 is equal to 0 in this modular arithmetic. So I want to find what is the multiplicative inverse of E. So I just guess. So if I just start guessing possible values for D, looking for a result of 1, I'll see that here it was getting bigger and bigger. Here it wrapped around. So I missed this time and hit 3. So I need to go around a few more times trying to hit that 1. And by the way, as you probably saw in the binary games, it's not always possible. Like if your modulus is 8 and you start with 4, there is no way to get to 1. 4 times 2, 4 times 3, 4 times 4, you're never going to hit 1. Not every number has an inverse. All right. But there are some mathematical properties for numbers you choose here to ensure that an inverse does exist. If an inverse did not exist, this encryption scheme would not work because you would not be able to reverse the encryption. So you have to try larger and larger values. And if you just guess and try larger values, you'll find that 53 works. This is a very simple brute force way to find it. There is a faster algorithm, but there it is. 53 is the inverse. That is the decryption key. So if you encrypt stuff with E, you can decrypt it with D because you can't divide. All you can do is multiply. So now we're going to encrypt a message. So Megan has a public key of 161.5, and that's what we just did. That is N and E. Those two numbers are your public key. And if Qball wants to send you a message like this, first you have to turn it into numbers, of course, using some algorithm. I'm just going to use ASCII, and I'm just going to make 3 numbers. And since I'm using really small numbers, I'm not going to combine them into one big number. I'm just going to encrypt 3 separate blocks. My block is going to be 1 byte because I can only encrypt numbers up to about 130 with these low numbers. But that'll do for an ASCII character. So in order to encrypt something, you take the plain text to the power of E mod n. So that is right here. Just encrypt each letter separately. And here's the encrypted message, 151, 119, 157. Those are the 3 letters. You can send those to the recipient at the other end, and the recipient at the other end can decrypt them by taking it to the power D. So first you took it to the power E, then you take it to the power D, because you can't divide. All you can do is multiply more. That's why you needed to find that added multiplicative inverse of E. So y to the E to the D is y to the E times D, which is y to the 1. That's the game here. So you can decrypt it by using the decryption key of D. And when you do, you get those 3 values, and those are the ASCII values of the message. H, I, and question mark. H, I, and punctuation mark. So that's how it works. And the math is really very simple. You just have to do it for very large numbers. So I made some challenges here. So calculate Qball. You decide to use these numbers to figure out the public and private key. And then Megan sends a message to him using his key pair, and you can decrypt it. And that's the very start of our essay. Now, of course, this is completely useless because these keys are too small, and anybody can crack this stuff. So something more realistic is here. Let me make this bigger. Okay. So let's move up a little bit to a short key, and then we'll talk about formats a bit. All right. So here you go. Here I'm going to take this key. This is also not secure, but it's better. This is up to maybe 10 or 15 digits long. So you can find the private key. So what you do is you can factor that number. And here you see how hard it is to factor something. You take the square root of something. And when you do, you're going to get this number. Now, the first problem is you haven't got enough decimal places to do this kind of math, so you have to use some high-precision library. Python has libraries for everything. Here I'm going to use math.squirt to get a higher one. There are many different ways to do it. But here, I'm going to just check the first 20 candidates. A simple answer is, see, you can try dividing by n. So you find the square root of n. And then you just try going down from that. This is as fast as anything else. You're going to have to try all the factors up to the square root of n. So I start at this and I just go down, starting at the known square root number and going down by 2's because there's no point trying even numbers because they're not prime. I'm trying all the odd numbers from the square root on down. And if you're lucky, you won't have to hunt too far to find it. You can see how this is really not going to work for big numbers. And that's the point. In this case, it works pretty soon. You can calculate this modulus very fast. So what I do is I take my guess for a prime number and I print n%i, because n is p times q. If I find p, n%p will be 0, because it's an integral multiple of p. If it's not 0, it's not the prime factor, and I find it pretty soon here. Because this is a common mistake in academic exercises anyway. People can choose p and q that are near each other. That is one of the mistakes you can make. And if you do that, then people can crack it. There was a capture the flag contest about 2-3 months ago where they had a private key that was, I think, 1 million digits long, a public key that was 1 million digits long. And it was the product of 2 companion primes, 500,000 digits long. So I found them quite quickly, and then I had a message to decrypt, and decrypting the message was going to take 7 days. Because you had to take a 1 million digit message to a 1 million digit power, modulus a 1 million digit number. And Python can do that, but it gets kind of slow. So I found a faster version of Python libraries to download to get it down to 2 days. And I started it and went away for vacation. Then I snuck in the building, and of course it had gone to sleep and crashed. But I had enough time to do it another 2 days. It was a 10-day long CTF. I think that was the last easy CTF, which I highly recommend. By the way, my students do the easy CTF, and we've never won it. It's every year. It's very good. We struggle. A bunch of them I've never solved, and that is intended for high school students. And I wish I had been to these high schools. I don't know who is writing this stuff. They're far more advanced than any college professor I know. But the reason it's easy is not that they're all easy. It's that there's a lot of puzzles, and some of them are easy. So your beginning students, some of them are just like these binary games. Very simple things, or like the stuff in your booklet. There's a message there. It's just in binary. All I have to do is change it to ASCII. There's a few of them. So if you're a beginner, you don't feel completely like you're lost. But they get harder and harder until they get really hard. And it's very educational. Anyway, easy CTF. Yeah, if you want to do a CTF, this is the best one. Although I've got them, I list them on my webpage a lot, but this is the one that runs every year. There are 2 really good things about it. The first thing is the puzzles are easy. The second thing is it runs for a long time, like 10 days. So you don't have to stay up all night or something ridiculous like that. You can wait till you have time. By the way, before you do this, another thing I should mention in this regard is Pico CTF. This is great. This is a real competition from Carnegie Mellon, but after they finish the competition, they archive it and leave it up forever. So you can just do it. And it's in the same spirit. It starts with really easy puzzles and has a little harder and a little harder and a little harder up to super hard. So everybody, like what I've tried to do in this workshop, everybody should be able to find something new and not feel lost. So this is where I tell my students to go before they do real CTFs, is go through this thing. It's very nice, very gentle, and Carnegie Mellon had Parliament of Pwning. They were #1 for years in all the CTFs. I imagine they still are, but I don't see that particular team around. But they just were a mile ahead of everybody. It was like Secretariat. I don't know if you guys remember. There used to be, I didn't watch horse racing much, but I think in the 70s or 80s there was this horse called Secretariat, and it was twice as fast as every other horse. It was just amazing. They had the Kentucky Derby. Bang, they'd run, and this one horse would just go whoop, be right here at the end while the rest aren't even halfway. It was amazing. And that's what Carnegie Mellon's team is like at CTFs. Everybody else has 1,000, they got 4,000. They make you feel sick. But anyway, their training products are available to us all, so yeah. Oh, the National Cyber League is much easier again. The National Cyber League is like at the Security Plus level. I've had a couple students do it. I'm not sure any of my students did it this year. I felt like the National Cyber League is so easy. It's too easy for my students. It's really just sort of like multiple choice question at the Security Plus level. They now have supposedly a certified ethical hacker level too, but I haven't tried it. Have you tried it?
Yeah.
Oh, good. Yeah, I haven't got my students too interested in it. I think Pico CTF is a little bit harder. But, and the real CTFs are harder yet. But, and of course the DEF CON CTF and the qualifier for the DEF CON CTF are just so hard, you just cry and go home and give up. I mean, it's like, I'm never going to put my students through that. This is like getting in the ring with Muhammad Ali. The only thing you learn is I'm never doing that again. I remember I did it like 7 years ago, and the easiest puzzle was like a clone of Twitter, and I couldn't get anything done. And I was cycling from coffee shop to coffee shop trying to figure out, I thought it was my internet connection. Finally, at the end, I realized it was, you had 1/10 of 1 second to do everything that would hang up on. That was by design. You had to script it all, do it all fast. And I thought, well, I lost the connection again. What's wrong with this? And you know, then the other puzzle was 42. It was a file. It was zipped 42 times with different compression algorithms. So I got 7-zip and got like 10 unzips. And then it was using like obsolete deck tape zips from like 1970 and stuff like that. And so like, oh, geez, guys, you know, it's really hard. It's hard enough that it's not even fun for me and people at my level anyway. But there are easier ones like this. This one's fun. Easy CTF is really fun. And there's a bunch of them. If you want more, there's CTF Time. CTFtime.org is a place where they post solutions and they announce upcoming CTFs for all of these. And there's actually a Russian team on this, and they're having a big dispute with one group who accuses them of cheating. But anyway, they post all the upcoming CTFs here. Most of them are way too hard, but they do have solutions and stuff. And what I do, like this PAC CTF is online, I think now or soon, and that's supposed to be one of the easy ones, like easy CTF. So for my students, I've always put them on my webpage, and we form teams and compete in a lot of these. I know they're doing the CTF here, and they said the one here is pretty hard. We just came from another one at Cal State University near Los Angeles, and that one was pretty easy. They got 3rd place in that one. But anyway, I put them down here. The NCL is happening, and I think, well, I might have some students in it. PAC CTF is coming up, and MITRE is coming up. These are pretty easy ones. I try to put it here if they're easy or not. And anyway, I highly recommend those. They're really valuable. This is where you really learn the real stuff. Far more than stuff in college textbooks, for example, which tends to be out of date and useless, as you may have noticed. Anyway, so that was the first RSA, and I wanted to say, and here's how you, so that was how you crack a short RSA key. Let me see if I finished that or if I got distracted and didn't. Yeah, so you put it in Gimpy, you can, and once you've got it, then you can encrypt a message. Yeah. Anyway, I don't think, there's more challenges down here where you encrypt this thing, and eventually, here's a public key there. You have a public key, and you have a message, and you have to decrypt it without the private key. So you have to factor this thing and find the private key. So that's a realistic problem, and it wouldn't even be possible for something this short if they didn't make a mistake of using prime numbers that are near each other. So that's the game. Here's the even longer one. And again, you can do it, although you have to make more precise square roots. It turns out you can do some of these pretty well. But you really, the original RSA recommended 512 bits, which is about 100-digit prime numbers. Now they recommend 4096. That's what the NSA says we better start using now. And that is a temporary measure to get us through the next 5 years until they develop crypto-resistant algorithms, because even 1 million digits are not enough to withstand quantum cryptography. So that's the first. The one other thing about RSA, I was been very frustrated about RSA for years because you never see keys in that format. You always see this kind of stuff. Begin RSA. And I have said, what is that junk anyway? And it turns out it's not actually documented in an easy way. There's an RFC that tells you what it is, but I suppose you people have tried reading RFCs, and so have I. They're very hard to understand. They have far too much data per sentence. So anyway, I went through this and found out what they are. So that thing is a, you can parse it here. With this OpenSSL, we'll parse it with ASN1 parse and show you what's in there. That's a base 64 encoded blob, and here's what's in there. N is the product of P and Q. Here's the encryption key, here's the decryption key. It's all the RSA values, and you can get them out with this tool and turn them back into normal hexadecimal numbers, and now you can use Python and multiply them and divide them and do all the math on them. So that made me feel better. This is the private key, of course, because it includes P and Q. P and Q and D are all secrets and should not be exposed to the world. The only thing public should be N and E. And so you can get the public key out of here, and when you do that, you just get N and E. The modulus is N, and the exponent is E. And if you run OpenSSL by default, it makes 512-bit keys because that was the original recommendation by RSA when this was all invented 20 or 30 years ago. And back then, that was considered secure. It's not considered secure anymore. 2048 was recommended until about 2 years ago, and then they upgraded that to 4096 now. So that's the game. So you can make longer keys by just putting it here. So here's a 2048-bit key. It's bigger and just in the same format. And you can also encrypt the private key. You can encrypt it with AES 256 so that it's stored locally with a passphrase. So if somebody steals your computer and gets the file, they still can't get in. So that's fine. And there's a couple different formats for it. But anyway, what I did after this, I made a challenge where first you have to go in here and find P, which is just right in there. And then you find the public key from here. And then I redacted this. And you have to find the missing pieces and rebuild it. And I did a challenge in one of the CTFs recently like this too. At first, this might look impossible because that's an awful lot of missing bits. But remember, there's like 5 numbers encoded in there. So it turns out that only a few bits are missing from the end of one of the numbers. And you can brute force it. It's funny. What I thought was funny, I did this and I got brute forcing working in Python. And because you can do modular arithmetic really fast in Python, I found it in like 10 seconds. And some student said, it's taking me hours and I can't get through. And it turned out he had the right algorithm, but he wasn't doing the modular math to see if it was right. He was sending the web request up to this form to see if it was right. And he got in after like 3 hours that way. Because you only have to try like, I think, 6 hexadecimal digits, which is 4096 times 16 or 256. It's a big number, but it's not an impossible number. But if it's that many web requests, it takes a while. But anyway, all right. So that's RSA. There's another thing worth talking about, which is signing things. And this is the Existential Forgery Act. Remember the padding oracle attack, which did not let us find the key and open the encrypted message. It let us trick someone into thinking we had the key and constructing a message which would decrypt to something we wanted. So we could impersonate someone that knew the key. And here is a similar issue. People use RSA to sign things. As you know, digital signature standard, that's what you do. You sign something, you take a document, you hash it, you encrypt the hash with your private key, and you publish it, and anybody can decrypt it with your public key. So anybody can verify that the holder of the private key encrypted. That's an RSA signature. And an RSA signature is just a exponentiation operation. So there are a few defects in it. And here we're going to play with it. So make yourself some RSA keys. This OpenSSL command generates them. Then you can ASN parse them, and you'll see as before, you have N, E, D, P, and Q. So you have some parameters. You can now play with them. Now, if you want to sign a message, you create a key pair. You then write a message. The message is X. And to sign it, you take X to the D mod N. That signs it with your private key, which is D. Then you publish that. Anybody who wants to can take that to E, and they'll get the original message back. So everybody can verify it. That's fine. So here we create a message. There's the message. You encode it, and you make the signature. There's the encoded message, and then you sign it by taking X to the D mod N. And by the way, if you use X star star D %N, it will take forever. You have to use the POW function. The POW function is super fast, because there's a smart way to do this, like you did in that little thing, the binary games, where if you're going to multiply things together and then modulus them, you modulus each term to make it smaller and then multiply it together. There are a few tricks you can do. Another one is square and multiply, where you calculate a table of squares and then combine them to assemble the number you want, instead of taking one number many, many times. So instead of taking a number to like 150, you square it, square it, and square it. So you have it to the 2, the 4, the 8, the 16, and then you multiply a few of those together to build the 150 you want. That way you only have to do a small number of multiplications, not 150. And the bigger the numbers get, the larger efficiency matters. And the POW function here is efficient. So if you use the POW function, you now have a signature. This is the signature for the message E, or with the exponent E. And you can verify the signature by taking S to the E mod N, and you'll see the string. So back comes your message. So that's what you want. So this is all fine. But you can do an existential forgery attack. This is a twist on it. So the question is, what could go wrong? And it's always the case. The math is fine. It's your assumptions that are wrong. Suppose I'm the original purpose of the math was I write a message and I want to assign the message so someone can verify the message. Now suppose someone uses it in practice and they don't care what the message is, they just want it to come out valid so that it'll prove that I am authorized. This is how I think some Java library used it. So here's the game. You choose a signature and you create a message so that the signature will work. You do it backwards. So I can decide I want the signature to be F, and I can calculate a message which will match that signature. The ASCII message is garbled nonsense, but it will work. So the point is, if I send this to a human, they will verify the signature and then try to read the message and it will be garbage. But if I'm talking to an automated system and they just want me to prove that I can create a valid signature, I can create a valid signature this way. I can just pick the signature and then pick a message that matches it. This is what happens. People misunderstand cryptography. It happens all the time. So they will compare these two things at the other end, and if they match, they'll say you're in. And I think in the same spirit, I'm going to show you this SAML thing, which is fun after this, which is a simpler version of the same problem. But anyway, that's the point. So here, sign with your name. The signature will be your name. Create a message that is correctly signed with your name as the signature. This is a very easy task. And this is one that offhand would be impossible. Now you have to, I give you the, take your, use the same key and create a signed message with your characters in the plain text. The only way to do this is brute force. You can create a whole bunch of messages that have your known signature and just run through them all until you find one that happens to have the right letters in it. So anyway, that's called the existential forgery attack. You can create a matched pair if you're allowed to vary the part of the operation that was not expected to be varied. And in the same spirit, let me show you this SAML attack because that's good, clean fun. This is something similar happening in the real world. I think I showed it to the gang yesterday too, but it's good to see. This is Burp. I'm running Firefox through Burp so I can see all the requests and replies. And all right, I want to make it so it does not intercept things. Okay. Now I'm going to go to Firefox and go to my demonstration page for this, which is SAML. Okay, so let's get rid of this. All right, so this is a very simple version of what happens on the web all the time. I have a service provider and an identity provider. You might have a service provider like a game or something, or an email client you're using where they serve up some kind of data to you and they have to know who you are to decide if you're allowed to see the data. Now, many people do not want to run their own identity provider. They do not want to handle passwords and thumbprints and whatever it takes. They want to just outsource that. So they have a button that says log in with Twitter or log in with Google or log in with Facebook. Everybody's doing this. So here's how it works. You have a service provider here. Mine is sp.samsclass.info. And when you log in, so you're not logged in, the kitten is asleep, so you log in. I give a couple of accounts you have to use. User 1 and PWD is one of them. So when you log in, you put user 1, you go over to some completely different website, like it might be Facebook, and you're logging in at the identity provider, IDP. It's a different server. Mine's on the same server, but it's running a different copy of the software. So now I log in here. The identity provider gives me a token to prove who I am. I now return to the service provider and provide that token. And then I'm now accepted. I'm logged in as user 1. Now, to win this challenge, you have to be admin. So you have logged in, but you have to elevate yourself to admin. Now, there are two ways to elevate yourself. One is to hack the identity provider into giving you the admin's token. Now, that would probably be difficult because they're probably somebody like Facebook or something, and they actually have professionals setting it up. The other way is to fool the service provider by modifying that token. And if the service provider is sloppy, and they're much more likely to be sloppy, they might not really verify all the data correctly. So that's what happens here. So let's just find out how this works. And I'm going to look at it in Burp. So Burp shows you every request and response that builds every web page. And you can modify it too. So I'm going to clear the old stuff. And I'm going to first just log in and watch the process. So I log in here, user 1, PWD. And I log in, and now I'm logged in as user 1. So here's what happened. I started at the service provider. I sent a request. It said you're not logged in, so I had to go to the identity provider and send several requests, ending with a token. Then when I come back to the service provider with the token, now it knows who I am. Now, what actually happened here on this post is to prove who I am, I sent up this thing called a SAML response. This is the normal way this is done with security assertion markup language, and this is how it looks. You have this horrible long blob of base64 encoded stuff. Now, you can decode that stuff in Burp. Let me start that way. You can right-click and send to decoder, and Burp has a decoder tab, and there's that junk. You can smart decode and then decode as base64, and it will turn into this readable XML stuff because SAML is XML, but you encode it with base64 just to transmit it over the web. All right, and so in this, there's a lot of junk in here. Okay, but at the end is the username. Here's the username. Some places the user email address and so on. So what this is a security assertion. It is saying I am this person, and all this junk up here is proving it. You can write your own Python code to unpack this, modify it, and repack it, but that turned out to be so important that people wrote this thing called SAML Raider as an extension for Burp to do it automatically. So if I go here, there's a SAML Raider tab, which will let me do common attacks on SAML, because SAML is really important. And on top of that, SAML had some really bad vulnerabilities a few years ago. There were 14 SAML frameworks, and 11 of them were vulnerable. They didn't do any of this stuff right. And this tool was here to easily try those attacks. So I can do attacks here, but down at the bottom, I see the structure of it. This is the same XML you saw before, now laid out a little more nicely. And I can zoom it up for people in the room. You have certificate, then you have a signature, then you've got another signature and another certificate, and then down at the bottom you have the assertion. I am user 1, here's my email, here's my name. That is what I'm claiming, and all those signatures prove it mathematically. So if the service provider correctly does the math and compares those signatures to what they should be, they can verify that I really am this person. Okay, so let's play with this. The way to play with it is to log out, get ready to log in again. Now, I'm not going to try to hack the service provider. If I was an underage person trying to get into a bar and they check the ID, there's two solutions. I could go to the DMV and hack them so they give me a real driver's license I'm not entitled to. And that would be difficult. Or I could just make a fake driver's license that's good enough to fool the doorman, and that would be a lot easier. So that's what we're going to do. I'm not going to attempt to fool this system. I'm going to give it a valid name and password and get a valid certificate for a different user. And I'm going to modify it. So I turn on intercept, so it will block the traffic. Then I log in. Now I can examine the traffic. Now the first packet is not interesting to me, so I forward that one. The second packet is the one that contains this SAML response, and I want to modify the SAML response. So this is the one going to the service provider, handing up my ID card for examination. So before it sends it to the service provider, I'm going to mess with it. So why don't I just change user 1 to admin? This is like taking white out and covering up the name and writing your name on the ID card and then presenting it. Let's see if that works. If I turn off intercept, the process completes, and I get an error message. I get an exception saying reference validation failed. So it's not that stupid. I can't fool it with that attack. It did some kind of comparison of those signatures and figured out that this is no good. So let's try again. Let me log out and log in again. Again, I'm going to use a valid account here because I don't want to attack the identity provider. I just want to attack the service provider. So I'll intercept again and go here. So now I'm user 1. I forward this one, and here's my SAML assertion. Now here's another thing you can do. You can remove the signature entirely. Now I have an unsigned assertion. And if I forward that one through, it accepts it, and I'm user 1. This is what's called a fail open vulnerability, and it happens pretty often. They did some kind of algorithm to check the signature. Is the signature calculated junk equal to the right calculated junk? And they forgot, what if it's entirely missing? That creates an error condition. They mishandled the exception, and they interpreted that as success instead of failure. And this happens pretty often. If the developer doesn't really think about the case when something is just missing, then you get unexpected behavior. So since it let me in as user one with no signature at all, that rather implies that I could probably be anybody as long as I have no signature at all. So again, I give it a valid name and password, and I go to Burke, intercept that. All right, I let through the first one, so the identity provider gives me a certificate, then I remove the signature, and now I change myself to admin. And now I let the traffic through again, and now I'm admin. Because they aren't validating, a bad signature won't work, but no signature at all will work. And I must say, I see this a lot, like people go to ID, they have a driver's license in another state, they don't know what that's supposed to look like. You could just make something. One of my friends from Germany had a international driver's license. He was driving around America. He said, guys will pull me over and they don't believe me that's a real driver's license. It looks pretty funny. It looks kind of like a passport. He said, this is a driver's license. It is. And they said, that doesn't look right to me. How would they know? I could just make any kind of junk. Anyway, so I thought you might like that. That's similar to this. You create some situation which will fool the provider at the other end that just compares your signature to see if it passes a validity test, but they don't really try to read the message, so they never notice that you're actually signing garbage. All right, and here's one where you go through the process of finding large primes, and here's one where you factor large numbers. But again, the trick here is just that you can only do it if the two prime numbers used to create the compound prime were similar. If you actually independently got random prime numbers, then no one could get in. And if you care about that, that's here, how to find large primes. Here I go through one of the older ways of doing this. First you have to get a large number. So here's a number 1024 bits long and is prime. And so you can find the next prime. This number is not prime. Find the first number above it that's prime. And the trick is you can detect whether numbers are prime with this test. This is the test. You choose a random integer and you do a simple calculation on it, and that has a 50% chance of detecting a prime. In fact, this one is right like 99% of the time. So 5 cycles of this is enough. There's a series of tests, and this is the Fermat primality test I'm using, which is one of the many. So this is a very simple test, and it has like a 99% chance of detecting if a number is not prime. So if you pass it 5 times, you're pretty much prime. So this is how it's really done to find prime numbers. And in case you feel like worrying, it turns out that there is a serious flaw with all of these, which is there are certain numbers which pass the test and are not prime. They're not very common. You won't get them by guessing random numbers, but you can carefully construct numbers that will pass the test and not be prime. And that means there are holes. Everything always has holes. Anyway, let me see what else is worth telling you about. I think you've been through all these, and we've got about half an hour left. Let me see what else I've got in the other one I might want to show you. I might show you the image magic exploit. That's kind of fun. Again, this is very much like what's happening with Drupal right now. So here's how it works. And you can do this one if you like. It's over on the Exploit Development Challenge. So first you get an image to play with. Let me just get rid of Burke for now. All right. And let's find an image like, for example, there's an image. Let's save that. Save image as, okay. Desktop. I'll put it in downloads. Okay, downloads. BSF 17. Okay, good. All right, that's a ping image. So what I did here was I just took somebody's public code for making an image processing for them, and I put it on an Ubuntu server that's an old version without patches. So I have the old vulnerable version of Image Magic on here. So I choose my file, which is on my downloads folder, and it's the latest thing in that folder. Oh, give me a break. It's the thing named BSidesSF. Why can I not find it? Well, I thought I put it in a downloads folder. Maybe it is on my desktop. Nope. I put it in a downloads folder, but somehow errored. Let's find it here. Show in Finder. Come on. Show all. Where is it? Why is nothing working? Oh, this is open. Okay. Show all. There. There it is. Show in Finder. There it is. Okay. It went to some goofy folder. It's in the CH folder. Download CH. Oh, okay. That's doable. All right. So here's my processor. I choose the file. Now that I figured out where my image is, I'll go to Downloads and CH. And there's my glorious image. Okay, now I upload the image. And it creates a thumbnail version of the image. And when you click the thumbnail, you see the full-size image. This is like everybody's profile page and image hosting website and everything. So everybody needs this, and everybody used this library, ImageMagick. And here, I added this so you can see the actual command that's being executed. That is the command, the convert thumbnail. Convert is the command to make a thumbnail this big of that image and put it here. That's what's going on to create this image. Okay, so now what you do is the vulnerability, you make a file with this and you make it look like a graphics file. So I just make a plain text document containing that junk and I save it. Let's put it in the same folder, downloads CH, and we'll call it exploit.ping. You have to give it an image file extension so it looks like an image file to the server, but it's not. It's just a text file. So when you send that file up, which is exploit, and upload it, what happens is it doesn't really form a thumbnail, but it does print hello and the date. So this is what's going on with Drupal right now. I can put commands right there and they will just execute on the server. Now the reason this happens is because you have a sloppy programmer that doesn't learn how to stay inside one language. In fact, for a more concrete example, let me just show you another one from this because we got a little time here. Here's the classic example of a command injection vulnerability. You'll find this on the diagnostic page of your router most of the time. There's a form and you can type in an IP address or a domain name and it will ping that to see if you have an internet connection. And this is written in some kind of scripting language like PHP or Perl or something, and whoever wrote it didn't know how to make a ping from in that language. So if I send a ping, all it does is take the real command line and put ping followed by whatever I put in. Then it pings two of these. So what you can do is you can just put in an address and then semicolon ls. And then it does ping that thing semicolon ls. Because it's using PHP to create a command line which it then executes in bash. So it's often very convenient. I do it all the time, as a matter of fact, but my servers are supposed to get hacked. Rather than figuring out how to do things in one language, you just build a command line and pass it to the system. Just execute it as a command line. But if you do, you can just do anything you want on your system by just putting more and more commands there. And that's what's wrong with Drupal now, and that's what's wrong with ImageMagick. So I can put real commands there. I can do anything I want. So I made a little challenge here. If you put your name in this file, it will put you on the Windows board. It's got a cron job running that looks to see if that file exists and puts you on the Windows board when you make it. So as you see, a bunch of people have done it. So, and I've got old winners too, you know. So it's good, clean fun. That's the simple command injection vulnerability, and it comes and goes. And of course, that's a simple kind, and the real king of it all is, of course, SQL injection. This is the one that is so famous because it's responsible for something like 99% of all the stolen data in the world, because people routinely give you I go to the tutorials, people routinely give you databases with forms that you can type into. So here's a search for a username. And if I search for this name, Herp Derper, I find that guy. This is Spider Labs test database for one of their products. Herp Derper apostrophe gives me a syntax error. So when you get a syntax error, that means you confused the server about the difference between data and commands. And that should not be possible. Nothing I should type in should ever be misunderstood as a command. But with command injection, it is. And with SQL injection, it is. So you can carefully craft a command, like, of course, this is the famous one, that will just use an apostrophe and then add another. So this is my name. So when I put in a name like that and submit it, what the developer wrote was this command, and what I put in was that name. So that should have looked for that stuff in the database, but it was misunderstood because it was parsed where this apostrophe matched that one, and it executed this union select command and gave me all the data. And this is what happens to everybody. It's just the most common case in SQL injection, but these other things have the same problem, where there is some way to get it to misunderstand the input as a command. And so that's where I start, because that's exploit development. First, you start with simple exploits like this, and then in the next course, we do the binary exploit development. Let me point you to that one. That is this one. And here, see, for simple cases, and here we go through the Shellcoder's Handbook. I'm doing this one right now online. I got like 280 students, but I thought that would be all right because only like 40 of them are turning in any homework. So it turned out to be doable. One thing, though, is I have no idea who most of them are. So you already put up scores by student ID, but these people are not official students. They're just everybody in the world. So I took the MD5 of their email address, and that's their score. And these people have already finished the course and got an A. The rest of them are on the way. These people have a B. They're on the road. People are doing pretty well. And it's just like these things you're doing. There's a series of quizzes online and chapters, and there's video lectures, and then there's a bunch of projects, which are just like what you're doing. But the point of this is exploit development is the process of taking a denial of service exploit and turning it into a remote code execution exploit. First, you fuzz. You send random junk to the server until something crashes it. Now you've found a weakness. Now you have to somehow carefully attack it so that that weakness turns into something more interesting than just a denial of service. And so for this stuff, you do not have the command injection type of vulnerability. What you have is you have to inject assembly language. So this is, for example, typical buffer overflow, like this one here. If you have a program like this, that just turns off ASL. Okay, here's the program. So I have a main routine that takes a command line argument and then calls a subroutine called copier, which copies it into a buffer that's only 100 characters long. So if I put in more than 100 characters, it will overrun the buffer. And this is the classic aleph null type of buffer overflow exploit. All these things are largely because of C. C is a very strange language because you have to specify how big things are. And when you use it, it does not check to see if you're wrong. So you can say, give me a 10-gallon bucket. Yes, sir. Put 100 gallons in it. Yes, sir. There's no problem doing that. Visual Basic would not do that. Python would not do that. They would just make it bigger. C will just do whatever you tell it, no matter how stupid it is. So you can do this. And when you do, of course, you can corrupt the memory and take over the machine, but you have to do it carefully. So if you just send too much data, it will just crash the server. You'll get a segmentation fault. That's a denial of service attack. But now the goal of exploit development is to improve your attack into something more interesting. So you run it in a debugger so you can see the structure of memory, and you run it, and you can see the stack pointer and the base pointer. Every process, every subroutine you call has its own section of memory, and it goes from the EBP to the ESP while you're in there. So right now I'm going from 3B0 to 428. So I can examine the stack in binary, and here's what you have. What I did to get here is I ran the program, and I put just a single letter A in. So it's fitting in, it's not overflowing anything. So if you look at the contents of RAM, you find the A I put in there. It's a 41 in hexadecimal. Then you have other stuff. Down here is the saved instruction pointer, and this is why these things work. You have a stack frame, which is the highlighted region. This is the memory used by the copier subroutine. If it returns, it will then return to this address when it's over to resume execution. And the goal of a buffer overflow exploit is to fill this up, overrun the buffer, and change that return address so it goes somewhere else under my control. And that's what we're doing here. So If you overflow it with a lot of 41s, you get 41s there. So this is the crash. The crash is because 41, 41, 41, 41 is not a valid memory address to execute. And now you can move the instruction pointer anywhere you want. And in this one, I just went and found shell code online. Here's a very simple shell code that's only maybe 32 bytes long that will just open a dash shell instead of a bash shell, which doesn't accomplish anything, but I can see it working. And so what you do is you build your exploit this way. You put a NOP sled, which is 64 nothing instructions, and then you put in the shell code, and then you fill in enough A's to hit the instruction pointer. And when you freeze it in the debugger, you will see this. I injected a NOP sled, which are instructions to do nothing. Here's the shell code I want to execute. Here's some padding, and there's the address. So I'm able to control this address. So now I put a value here that hits the NOP sled. And when it tries to return the subroutine, we'll go up here, do NOP, and execute the egg. That's how it works. So it's really the same as those other command injection vulnerabilities, but it happens at the hex level. So you have to read the hexadecimal and you have to know a little bit of assembly code, and that's why it's my most advanced class. But it's the same logic. That's, you do it at the binary level, and that's the game. So now you can run that thing. And so we go through this stuff, and there's that's the classic buffer overflow exploit from Aleph Null from 20 years ago. And of course, everybody took over everything for about 10 years, and then people started wising up and patching it. So now there's a bunch of defenses to stop it, and we go through other projects until we're attacking the latest version of Windows with attacks that still work, but it gets harder and harder. Microsoft has gotten very good. In fact, starting about 6 years ago, Microsoft wised up to where they stopped fighting hackers. The original theory is you hackers should just shut up and go away and not tell anybody, and everything will be fine. And they finally realized that's not going to work. So they started, I remember they bought us all beer at TorCon. And now they have their bug bounty program, and now they even have the blue hat program where they will invite you to come, and they'll pay you $100,000 by hacking into Windows, and they'll pay you another $100,000 to fix it. And the latest generation of fixes are from the attackers, and the fixes are getting very clever. So it's getting pretty hard to hack into Windows, and the way you do it, unfortunately, Microsoft their operating system is so big and sprawling that they can never patch it all. They have all these defenses, but the defenses don't really apply to every program on the box. Some of their own code has the defenses turned off, and all the legacy code from other developers has the defenses turned off. So what you do is you hunt for the weak spot, of course. But every generation is much stronger than the previous one, and you have to keep upping your game. I remember when we went from XP to Vista, they introduced data execution prevention. So when you eject data on the stack, it won't run, and address space layout randomization, so you don't know where you are. And that blocked the ethical hackers for a whole year. They couldn't not take over Windows Vista at Bowne that year. They had to give up and take over XP because none of that generation of exploits at that time worked anymore. And it took the good guys about a year to catch up and develop better exploits to get in. So, you know, it's good, clean fun to do this stuff. And I got some students that are getting the OSCP certification, which is the certification for this stuff. And they told me that, I think this one here, they said, this project is the one to do. You got to know this. This is what you have to do to pass the OSCP certification. This is following a blog, and so are they, I think. This is taking over Windows machine with all the defenses, with the right tricks. And there's just a step-by-step process, but you need to be pretty good at it. You need to be able to do it because of the remote exploit certification is considered so valuable because, like the Red Hat certification, it is not a multiple choice test. You know, Red Hat administration certificate, they stick you in a room with a box, you have 8 hours. By the end, it won't even boot up right now. And at the end of 8 hours, this has to be a web server, an email server, an FTP server. Have fun. And the OSCP certification is the same. There are 6 boxes, and you have to hack into 4 of them, and you have 36 hours. And then you have to submit a complete report of exactly how you got in so they can prove that you really did it. You didn't just copy it for somebody else. And it's not a multiple choice test. You have to really know how to do it. Anyway, what they tell me is this is pretty good procedure. This is the modern standard, modern way to get into Windows. And it's the whole thing. First you fuzz it by sending random junk until it crashes. Then you put it in a debugger, see why it crashed. Then you figure out how to inject code, how to find out where you are, how to run the code you injected. And then you use Metasploit to make a payload and stick it in, and off you go. All right. Anyway, is there any? Oh, the other thing, another question I forgot to answer that I always get is, will this stuff be available later? And of course it will. If you go to samsclass.info, what happens right now, of course, it's right at the top of the page because this event is in progress. After the con, I will put it on the old classes page here. And it will just stay up forever. So here's the stuff from Toro that happened a couple weeks ago. Stuff from previous DEF CONs is down here. Everything is there. So if you want to do these things later, you can. And by the way, everything is available for everybody to use. If you, I have a use policy. Everything is copyright free. You can do anything with this. You can show it to your friends. You can print it in a book, put your name on it, sell it, and keep the money. You can do any bloody thing you want. The only thing you can't do is commit a crime with it and expect me to save you. So, I mean, if you hack into somebody with this, God have mercy on you. But I don't care. Feel free. I remember when I did my first talk at DEF CON, I had all these projects for my ethical hacking class from maybe 10 years ago. And I was thinking, do I want to like actually try to protect this stuff from the hackers? I will just make a fool of myself. So I just zipped it up and put it on BitTorrent myself. I said, there, that's over. Now we can, now I don't have to waste my time. And then what happened is some guy, I named my class after the textbook because I was trying to hide from the college administration committees, right? I knew they would freak out when they saw I was teaching hacking. So I just used the title of the textbook, which was like ethical hacking, network defense. And anybody asked me, what are you doing? Oh, I'm just teaching a class from this book. It's a harmless class, nothing to see here, move along. And that worked. So what people did was they downloaded my stuff from BitTorrent, put it on a CD and started selling it as a CD copy of the book. And some guy emailed me, hey, you ripped me off. I said, what? I paid $30 for this. It's just this free junk for your website. I said, well, somebody ripped you off and it wasn't me. You should protect that stuff so nobody can get it and sell it to people like me. And I said, you don't understand how the internet works. But anyway, and now we got cryptocurrencies. If you really want to get ripped off, holy cow. Boy, I had a student, I was disparaging cryptocurrencies like I always do, saying, holy crap, this happened in the tulip bubble and everything else. People started paying $8,000 for Bitcoin. And I said, there's no way in the world that Bitcoin is worth $8,000. And my students bought in at that level. This is going to be great because there was an article with the Bitcoin experts, and 6 out of 6 Bitcoin experts said it'll be $100,000 next year. It really will. And then $1 million after that. Buy, buy, buy. And I said, I know why they're saying that. Don't you know why they're saying that? But see, I used to work on the fraud desk under contract to the Federal Trade Commission for pyramid schemes. So when they brought out Bitcoin, I said, dude, this is my life. I know pyramid. I used to be the guy in charge of analyzing the finances of pyramid schemes and giving the money back to these poor suckers, and I learned how they work. But we're having to learn again. Anyway, so my student bought in at 8,000, and I hope he sold the next week because other than that, he took a bath. Anyway, so I think I run out of things to tell you unless you got any questions. Yeah. Well, I think one of the you'll find it's too short. You have to find you'll actually so you just Google online resources. That's all right.
There's public cryptography. Any other like single basic things that can generate kind of world.
I've never heard of an attack like that. It doesn't seem to lend itself to that kind of attack because the idea is everybody has different numbers. Now, what happens though, many times, if people don't really all have different numbers, that came out about 8 years ago. Database researcher had a real simple research project. He just downloaded all the public keys from every HTTPS website on the web, and he found that 1 in 1,000 of them are you reusing the private keys. Right. And then they try to figure out how did that happen. And I think Dan Kniske talked about 5 years ago at DEF CON. That happened because the random numbers were not random. Because there's nothing random in your computer. So you buy a firewall, you turn it on, it takes so many cycles to boot up, it creates what's supposedly a random number, but really there's just a clock, and there's really nothing random, so it has a pretty high chance of you giving the same random number. And that is a huge problem. Where do you really get a random number? And there is no really good way.
Was there a company that puts out a device that uses reflection on air particles to generate a random number?
I haven't heard of that one. I know Cloudflare uses a wall of lava lamps, or at least they say they do. And I know that there's a hardware chip you can get for you can get an expansion card for a desktop computer. And what the electronics usually does is run current view resistor and then amplify the Johnson noise. So it is basically coming from the random motion of the atoms in the resistor. And that is considered high quality randomness, and that's built into the Intel processor. But at least BSD refuses to use it because they're afraid the NSA is backdoored. Not really. Quantum computing will not end private key encryption. It makes the thing that will end is public key encryption. Private key encryption, quantum computers will just be faster, but only to a controlled extent. So if you go from AES 128 to AES 256, you'll still be okay. The theoreticians have already figured out what they can do, and they can't crack private keys any more than that. They can crack a 256-bit key with only 2 to the 128 operations, but it doesn't get any smaller.
The whole strength of quantum computing is that it can make guesses just so much more rapidly than we can right now with yes.
It can, but there are limits to what that can accomplish. And what it was at Cloudflare Summit, they had the cryptographers from Berkeley. They were talking about this at Stanford. And there's an algorithm called Shor's algorithm, which works against RSA encryption because it factors the prime number into its factors. That they can do. But they cannot do a brute force attack any faster. So if you have an AES key that is just 256 random bits, there is no way to get it without doing 2 to 128 calculations, even with a quantum computer. So that's why they say private key encryption is going to stay with us. It's always been with us, and it will remain safe. But private key encryption has the huge problem of key distribution. Public key encryption was invented in 1970 and was the miracle solution to that problem. But it relied on this really shaky concept of a one-way function, where you can multiply 2 numbers and make the product easily, but you can't go the other way. And that was always weak mathematically. There's really no good reason you couldn't run that function the other way. And the quantum computers are really doing a lot of damage to that one-wayness. So there will be a new generation of encryption algorithms that are quantum resistant. There are currently 20 candidates, and one of them just fell last week. They proved that it was totally broken. But they're going through the process now. It should take about another 5 years. And then we'll have something new to replace RSA, which is quantum resistant. I actually bought some IOTA, speaking of cryptocurrencies, because they were the first cryptocurrency with an actual business case. They were going to let different things. It turned out that all their math was crap. They decided to make quantum resistant crypto too early. So they invented their own hash function. By the way, I haven't mentioned that in this class. Never write your own crypto. All you will do is immortalize your stupidity. I mean, the fact is, since Pythagoras, a small number of super geniuses have figured this out. And if you think you're smarter, you're just wrong. And if you thought up something cool in the shower, I'll shift every letter to the left one, and then moving forward one, that'll be great. You're wrong. They figured out all of those tricks 200 years ago and hacked them all. And that's why we ended up with stuff like RSA and AES. Don't be creative. Just use the standard stuff that works, or you'll really be sorry. And then, actually, they aren't kicking me out of here. Let me show you a fun crypto demonstration of Android. This one's always good, clean fun. There's a Android emulator, and I should be able to show you this one. Might just be here.
Is it virus total emulator?
Virus total what?
Emulator. Virus total is
I don't know about it. I don't know. Though this is Genymotion, which is an older one. I do not know if Virus Total had an Android emulator. They do it to run things and see if they're malware. That's a good idea. I know Google had one called Bouncer, and they hacked it. So anyway, here's this thing called Stitcher. This is some kind of music player. And let me run this through Burp. This is a good thing to show you. Burp, here Burp. Okay. So I run a Burp proxy and I started listening. Okay, and I want to listen on all addresses. Okay. Well, I really just want to use this public one, which I guess is 192.168.8.158. That looks about right. Okay. So let me send my Android traffic through that, which is, yeah, go away here. Okay. Yeah, get lost. So this is my Android machine, and I want to tell it to use that proxy. All right, I think I have to figure out how to kill Snapchat. It's going to drive me nuts. Apps. Here, apps. Okay. Where is Snapchat? Okay. Stop. Okay. Now, Wi-Fi. Okay. Modify. Okay, I'm going to go through 192.168.8.158. Just so I can see the traffic. Okay. Okay. Now, I bring up Stitcher. Okay, good. Here comes some traffic. Looks like my Stitcher is for some reason not launching. Let's get rid of that. Stitcher, I say. Where is Stitcher? There it is. Okay. Good. Here's some Stitcher traffic. Okay. So Stitcher is sending data over HTTPS. Now, if I sign in with my own account, I give it like a@b.com, and I put in a password of PASSWORD, and I log into Stitcher, then I will see a post here someplace. There we are. There. Post auth. That's probably it. And yeah. Okay, here's my parameters that are being sent up to Stitcher. And you will see something giving me trouble here. Okay. Maybe it's this one. Well, where's my Stitcher? There's my Stitcher help desk. All right, I'm losing my mind. Just a moment. Intercept is on. Oh, that'll do it. Okay. That's why it's waiting. Now, where's my Stitcher? I might have to just filter for Stitcher. This is too much other junk going on. All right, just a moment. I got to go to Target, Scope, Add Stitcher.com. Okay. Sure, stop sending out, and then proxy, disabled, yeah. Let's just clear old stuff. And now, theoretically, I only see it. So a@b.com, password, I'll put a 1 at the end and log in. Ah, now I'm finally getting somewhere. There, this is what I wanted to show you. Okay, it's sending the parameters up to Stitcher. Looks like they fixed it. This demonstration is going to be too annoying. I thought I had blocked updates on this thing, but it looks like they have improved their stuff. Stitcher used to be hilarious. They have their custom encryption, and it's just the Caesar cipher. And you can do it. And if somehow I got the old version, but if you put it in a password, it's fun to play with. You put in a password A and B and C, and you just see it changing. They added extra junk to make it look like an MD5 hash. There's an academic product used for teaching Cisco too that does the same thing. They don't have JavaScript that just takes your password, moves it with Caesar, adds a bunch of random characters to make it look like an MD5 hash and sends it up. There's a bunch of people that do this. They just make it look like they encrypted it. So, you know, there's fake encryption just like there's fake news. Anyway. All right. Anyway, I guess so. Yeah, okay, bud. Glad to see you. All right. Yeah, I hope that does you some good, and I'll stop this recording. If I can figure out how, stop share, end meeting.